Hello everyone, my name is Jonathan Harris, and yes, it's been a while. I took a break after GSER. I did one Botball analysis after GSER, but after that I decided to take a break. I've also been getting my own team underway, and now that things have kind of gotten started with them for this fall season, I feel like I can now start working on some Botball videos that I've been meaning to make for a really long time. I'm going to take a break from analyses for a while, and I want to start making a couple of tutorials helping beginner teams make their own complete library that will allow them to make almost any run that you're going to be making, or you're going to be designing or sequencing on at least the fall board. I can't really promise anything for the springboard, but I'd like to just make a fairly decent library that beginner teams can follow along and make this library and get these tools that are going to help them later on as they are working through Botball. And then I'll pose some questions at the end of each video about how you could make these functions better and increase their accuracy or performance with a lot of the same tools that we've already used. So today I want to make drive and turn functions. This is going to look at a couple things that are going to be super useful and foundational to use later on as we progress through Botball. Right here on the screen, I'm going to put a list of all of the different concepts that you're going to need to know in programming in order to follow this tutorial. They're very basic, and you should be able to understand what they're doing after messing with them for a little bit, even if you don't know what they are before starting this video. But without further ado, let's hop into it. Alright, here we are in the KISS IDE, and we are going to start by just going to our user and making a new project. We are just going to call this driving tests. So this should look familiar to everyone here. This is the default project. We're going to go ahead and delete print the hello world, and we are going to begin to look at what you guys already know. So everyone here should be familiar with motor, msleep. It's the three basic commands to make the bot drive around the board as simply as possible. Motor, msleep has quite a few issues. I'm sure many of you who are at this point have figured out. When you have a bot that is running off motor, msleep, you can sometimes find that it curves drastically. And so sometimes teams may even have motor speeds like this in order to just make their bot drive in a semi-straight line. But even then, because the way motor works, this is going to be different at different battery levels, and this is going to change constantly, and every time you try to change the speed, if you need this to be slower on both, then you have to refine the proportion for that. And it's just a really big hassle, and so we like to get rid of that as much as possible with the least amount of effort as possible. One of the easiest ways to do that is changing motor from motor to MAV. MAV is very similar to motor, but instead of just putting a power outage, like a power percentage from 0 to 100, towards the motor without any care for what is actually happening in relation to the motor, MAV is move at velocity. And this, instead of, it's the same thing. We have port and then speed. Well, port and velocity, technically. So we have port and velocity, but instead of this velocity being on a scale from 0 to 100, or negative 100 to 100, I should say, if I'm being more correct, this has a scale of negative 1,500 to positive 1,500. So instead of something like 50, we would say 750. That's my favorite speed to use when I'm using MAV commands as the driver for my functions. Now, this is going to help a lot with how much the bot changes over battery life. I've done a lot of tests, and it seems that MAV functions the same right when the bot turns on and all the way until the battery dies. So that is going to help you a lot. Now, one thing is, this doesn't make the wheels drive perfectly straight. There's a lot of work that goes into making the wheels drive perfectly straight. But this will more likely use something like 723, possibly, if you do your calculations correct. That's probably what your wheel speeds are going to be. But this is going to help you be a lot more consistent with how your wheels are in proportion to each other, just because they're not changing depending on how much battery life is in the robot. And so you can fine-tune these for each drive. But this is still very simplistic and not really a functions library, because I could sit here and I could paste this over and over again, but that's a lot of unnecessary repetition, and the whole point of a functions library is being able to compact this down into the cleanest code possible. And especially when we get into more complicated functions, it's going to be a lot harder to be able to do something like this. So we're going to make functions. Now, before we actually put the function in its shell, we're actually just going to write the function inside of the main sequence of code so that we can see what's happening. Now, the main hero of our drive and turn functions is going to be the get motor position counter. All right. Now, the get motor position counter is sort of like an analog or digital sensor in that you plug in a port for a specific value that you want returned. Now, the get motor position counter doesn't use the digital or analog ports on the Wombat, but it instead returns a value of the wheels inside the robot. So that'll tell you what the motor position counter is of that wheel at that position. So if I was to say something like this, which basically just is going to print the value of the get motor position counter for port 0 to the screen, we can now compile this and run that, and we can see that the value of the wheel is 17. Now, if I was to pick my handy dandy robot up over here that you guys can see, and I was to take that port 0 wheel and spin it a bunch more, then when I go back and I run this, it's now going to say 1821. This also works for the negative direction. So if I was to go twice as long in the opposite direction, making the wheel go negative, then we run this, we're going to see a negative value. So this is an accurate way to, an accurate enough way to measure how far the wheel has rotated. This stays consistent until you get over about 1250 to 1300 speed. Once you start breaking that mark, then your tick counter becomes a little inaccurate. So I would suggest staying under 1300 speed. That's going to help you a lot. So why would we want to use this tick counter like I've mentioned here? Well, here's the main benefit. Instead of the amount of time that your wheel spins being based off of a certain amount of time, it is now based off a certain amount of ticks, which can translate to a certain amount of distance. The reason this is good is because if I was to tell a robot to move both wheels at these speeds for 800 milliseconds, it would drive on the board a certain amount of distance. If I was to then change these to be something along these lines, now the bot drives an entirely different distance. And if you want to try to travel the same distance that you just did, you're going to have to go through and refine this value all over again. And I'm sure many of you have come across this problem when you're writing your sequence and you find a drive, oh, that's too long, or oh, that's too fast. Then you reduce the speed, but then your distance is completely off because you're using msleep, and so you have to increase that, and you have to refine these values, and it's a very slow and tedious process. But if you're using a tick counter, it doesn't matter what speed it's going at. You could tell it to move at speed 1, or you could tell it to move at speed 1000, and it's still going to travel roughly the same amount of ticks in the robot, but it is going to complete it faster. So that is a huge advantage of using the tick counter. So let's see how we can use the tick counter in a function. Well, obviously we want to rotate the wheels until they reach a specific point. That is the definition of a while loop. So we want to say while get motor position counter of a certain port is equal, so I'm going to use, usually when I'm going fast and making functions, will use the right wheel. While the get motor position counter of the right wheel is less than a certain tick value, let's just go ahead and put in 5000 like that. While this is true, we want to spin the motors. Now, when you're riding in a while loop like this, you don't need an M sleep. You can add one, and in some cases we will add one, but in this case right now, we are not going to be adding an M sleep, because this is going to repeat these two functions over and over again, and usually the only reason you need an M sleep is so that it will stall on these commands to repeat them. Now, if we're already repeating them, then we don't need the stall. Now, something a little strange here, like you might have noticed earlier, the tick counter saves in between runs. So maybe at the end of this run, I start at 4000, but I spin the wheels and move the bot around before I start the next one. So it's already going to be closer to 5000. So we need a way to reset the counter so we know we're starting at 0 on the counter and we are moving up to 5000. Well, that's fairly simple. All we have to do is say clear motor position counter, and then the port we want to clear, and that's going to reset the get motor position counter. That's going to set the ticks internally in the wheel that you've specified back to 0. So just to clarify, this is the port, not the number we're setting it back to. But now this will move both of these wheels until the tick counter is above 5000, or equal to 5000 in this case. Just as a precaution, I find it useful to lock the wheels afterwards. There are cases where you wouldn't want to do this, but for basic functions, it is very convenient. Oh, some of y'all probably caught that. I said 0 twice instead of changing the port. But it is very convenient to lock the wheels afterwards so that they don't drift to a stop. Because if your bot stops, the bots are told to stop the wheels, well, they're told to stop giving power to the wheels, they're not told to lock the wheels, so the bot will drift to a stop, and that's not very accurate. So we're just going to teleport the motor 0 to go speed 0. We're going to tell motor 1 to go speed 1, and we're going to do this for about 15, well, we'll go ahead and say 20 milliseconds. Now, this is a working function. There's a little bit we need to do to make it work better in an actual capsule so that we can use, but if we go ahead and compile and run this, we will see that the robot drives forward for 5000 ticks. So what if we want it to still travel 5000 ticks, but we only want to move at 100 speed? Well, it's still going to do this. It's still going to do this. It's just going to be slower, but the distance is the same. That's a huge power of this function. We can also increase the speed or keep the speed the same and get different distances just by changing this number from 5000 to something like 1000, and you'll see it drives a completely different distance. So we can already see how useful this could become, but writing this every time you want to drive would be very, very confusing and would muddle your code beyond belief. So that's not what we're going to do. We're going to put this inside of a capsule for a function. So we're going to go ahead and put that up here at the top. So we're going to say void Now the reason we're calling this a void function is because it is not returning any value, unlike our int function, that is the main right here, that is returning a value of 0. But since we're not returning anything, we're going to call this void. Now we're going to call our void drive, and right now we are going to do open close brackets, and now this, whatever's in between these brackets, is categorized as being called the drive function. I'm going to go ahead and keep writing, but hopefully this will make more sense in a second. So I'm going to move this code into here, and now I can hold this function here, and I can call drive as many times as I want, and it will repeat this function. And this looks a lot better than copy and pasting this code 3 times. So, but as of now, this is not very useful because this is a set drive at a set speed, and a lot of the parameters don't really help us. So we need to add, well, the parameters don't help us because there are none. We need to add parameters. So what we're going to do is we can add parameters inside the parentheses. We can tell the drive function how we want it to behave by giving values inside these functions. So the first thing we're going to do is we're going to say distance, right? We want to give a distance that the robot can travel. This is going to be the variable type, this is the variable name, and this is the variable distance. We are not going to set the value of distance to anything. We're going to hit comma, and we are going to give the next variable, which is speed. Now we've clarified 2 variables that we are going to be defining later when we call the function. So when I call the function, I can now say inside of these parentheses 5,750, and it will now translate 5,000 to set equal to the variable distance and 750 to the value of speed. So I can now implement distance and speed into my function. I can put distance here, so while the get motor position counter is less than the distance needed to exit the function, we want to keep moving the motors at this speed. Like that. So now this function becomes very useful. We can specify the drive, and when we want, we can change these parameters to get different behaviors out of our drive function. So maybe this time I want it to drive 1000 at speed 900. And now you can see that behavior working here. Now, there is still one more problem with this. Well, what if I need to drive backwards? Well, you very reasonably could say, okay, well then I would say drive. The distance is going to still be high, so we still want it to drive 1,000 ticks, but we want the wheels to be spinning in the negative 500 direction. Well, yes, that would make sense. But the problem is, let's go ahead and run through a sequence of what this looks like. We clear the motor position counter. We check, is the get motor position counter, which is right now 0, less than distance? Okay, spin the wheels. Now we look at speed. Speed is negative 500. So we move both of the wheels backwards, and now our tick counter is negative. In every loop of this function, it will become more and more negative, getting farther and farther away from our positive distance. And we can't just say negative 1,000, because that would be, in this case, would never be true. 0 is not less than negative 1,000. So what we can do in this case is say, while the absolute value of the get motor position counter is less than distance. So even if the tick counter is going negative, it's still going to be showing a positive value. And now we can go in both directions. Now we might have a little issue here where we're getting compiled with warnings. So that means we just need to do this. There you go. So now although the absolute value function is recognized in the Kibble Wombat library, and it will work. If you want to get that pesky completed with warnings message out of the way, it is important to re-include the standard library. Now we have our completed drive function. That's not too bad. And this can be used to make any drive necessary on the board that you're going to need. Let's go ahead and move on to a turn function. We're going to go ahead and start inside the function this time because we already know how to do it. So we're going to specify void, and we're going to call this turn right. We're going to specify, I don't think degree is the correct number, so we're going to go ahead and call this distance again, just because I don't think there's a more accurate way to say it. And then we're going to call speed once more. So we want the wheels to spin or turn right. And so in this function, we're actually going to have the right wheel go negative and the left wheel go positive to give us a 0 degree right turn. So we're going to do something very similar to what we did earlier, which is clear motor position counter 0. Because we're going to still be getting values. Well, let's go ahead and do a different one this time. Let's go ahead and get clear motor position counter of the left wheel because that is the one that's going to be going positive. So we're going to clear that wheel. We're going to say while that wheel is less than the distance we said. Now, keep in mind this time we are specifically calling this a turn right function. There is no turn left inside this function because turn left and turn right are going to be two separate functions. So this one's only going to be turning right, meaning that the value of this wheel is only going to be going positive, so we don't have to worry about putting this in absolute value. So while it's less than distance, we are going to say we want our 0 wheel to be going negative speed. We want our positive wheel to be going positive speed, just like that. And then we are going to lock those wheels afterwards, just like that. And now, when you call this turn right function, we're going to specify distance. Let's go ahead and say like that, and 750. You can see that the bot turns a specific amount to the right. So it's very easy to flip-flop this to the left. We're just going to copy and paste this down here. We're going to call this turn left, and we're just going to invert everything. Instead of being on the left wheel, it's going to be on the right wheel. So just like that. We want those ticks to be checking the right wheel now, and instead we're going to say the right wheel is turning at a positive speed and the left wheel is turning at a negative speed. So you can now see that working. And so now you have 3 basic functions that are going to be super useful for the rest of the time in Botball. Now, these are not perfectly accurate functions. To get perfectly accurate functions, you have to do a lot of work, and it's something that I'm personally working on right now, and it's extremely hard. So these are just ways to help you simplify your coding and get more accuracy than motor. This is going to help a lot, and this is going to get you started on the right track. And if you use the methods that I talk about in my Botball analysis videos, you're going to get pretty far. Now, like I said, I wanted to pose a question. I want to give the simple parts, but at least set it up in a way that you can at least get some learning aspect out of it, and I'm not just handing you over the code that you can use. This is still supposed to be a learning process. So let me ask you this. Right now, ticks is a pretty ambiguous value. When you're trying to measure how far you're going, you're just kind of guessing. Especially when you get into sequencing, you'll be like, well, that looks like probably 10,000 ticks. And your values are going to get pretty high if you have to drive long distances. How can we convert ticks into something useful like centimeters? And how would you go about doing that? If you could find how many ticks there are per centimeter, then when you make your drive function, you could specify, I want to drive 15 ticks. I'm sorry, not 15 ticks, 15 centimeters at speed 750. And then your function does the conversion to convert centimeters into ticks. But I'll leave that for you guys. And but to continue on that same vein, how many ticks when I'm turning in this way, how many ticks converts to degrees? How many ticks per degree? And how could I say, well, I want to turn right 90 degrees. How can I convert that into how many ticks my bot needs to travel? But I'm going to leave that for you guys to figure out yourself, because I think figuring out yourself is the best way to hammer it into your brain. So I leave that for you guys to figure out yourselves. I hope you have a wonderful day, and I'll see you next time.